studying section 6 turned out to be rather difficult. So before embarking upon the problems, I'll just report what I did to get on top of section 6. What I wanted was to do what Professor Koblitz did in section 6 with this curve instead, to prove to myself that I understood all the details. I went through the calculation of the last problem of section 5 twice to get the computation of the L function, and failed miserably both times. There were simply too many details of which I was uncertain, small steps I forgot or thought I remembered the result, and it went very wrong. Then I thought I could make the zeta function of the Eisenstein integers. That failed. Then I started on the Gaussian integers. But then I realized that I could actually do the theta function. And what you see here is the second time I went through with that. So that was not so difficult. So I could actually compute the value of the zeta function at 1/2. The formula I derived, and that was an integration of the exponential function. The exponential function here, and then I'll just make it larger for you, and then t to minus 3/4. So there's a numeric integration that has to be done, and then I get the result zeta of 1/2. And that's exactly what Paris gives. And also I realized that Maple itself has this theta function built in. So we all agree. I see I'm not quite exact, but that's just a question of getting a few more digits here, like 40, and then going through it again. What? There we go. No? Let's try. It won't do it. So we do them one at a time. Oh, it still doesn't agree. Maybe we should have added 5 on as well. Yeah, that's what we need here. And then it agrees, ending on 125. Right. So that was the Riemann theta function. And then I knew I had to take it upwards one step at a time. So I computed the zeta function of the Gaussian integers. That was the next step, which I have here. I believe this was the 3rd time through, you see here. Oh, I did it with sum alt, which is not very precise. I've learned later that, I'm not quite sure though. Yes, it has the Dedekind L functions, so we can get a correct result using that instead. I learned that later. So that was the Gaussian zeta function, and I got that to this result, which is exactly what we got up here, almost. Yeah, so that was right to 38 decimals. Then I was ready to do the zeta function of the Eisenstein field. And that worked as well. That took 2 pages. I checked the reflection formula, of course, just to make sure that I was on a solid footing. And then the reduction, again given an integral that has to be computed numerically, which we have here. And then, having done that, I was finally confident that now I would be able to do the L function for this curve, which we have worked so hard on in section 5. So I went through the mathematics, verifying the reflection formula, and deriving the value of at s equals unity. That looks very simple. So I really, was it really that easy? But we have to compute it. Here is the character chi we're working on, and then the value we need, and we can see that the result is real as it should be within the 40 digits we're working. So this should be lambda of 1, and I define the elliptic curve y squared plus x to the third plus 16, and initializes the L function on the interval from 0 to 2, and ask what is its value at unity, and that becomes exactly what we've got up here. Therefore, I declared myself pass. That's a pass on section 6. Now I'm prepared to solving the problems of it. There's just a question. I had to go to 9. You see, I sum over A and B, so I make a 2-dimensional sum, and in problem 6, or in section 6, they convert this to a one-dimensional sum, which we'll see how we can find the values EP. I hope that's explained later in the problems. That's a little difficult in the in this field where we are working, because we have Gaussian integer. We have Gaussian integer factorization in Mabel, but we don't have algebra in the Eisenstein among the Eisenstein integers. That's not yet introduced. I don't know if I'll be able to. Maybe I'll be able to do this with a one-dimensional sum, having solved the exercises of section 6. Maybe I won't. That was a report over my study. It was very hard because I had to master the method that I just was able to, almost reach during the exercises of section 5. May the 1st, 2023. Let's get started on problem 1 of section 6 in chapter 2. I've written up the formula of L of 1 from page 91, which we have here, and then we are told that 2AP minus 1 equals, I don't know how to read this out, I say P over N times square root P. So that means that this will be the product and let's divide by the square root of P. This was extremely simple. What a surprise. We have L chi of S is the product over the primes, 1 minus chi of P times P to minus S. And that's exactly what we've got here. So this simply equals L of this symbol evaluated at S equals 1/2. I don't know exactly what that tells us, but that solves problem 1. I still have the problem, by the way, because the function, I'll just write it up, converges, I guess, for real part of S being larger than 1/2, and the L series of En converges for the real part of S being larger than unity. And then when we insert unity here and 1/2, we may get a convergence, but do we have any knowledge that they are equal? I've had this problem already in an earlier exercise with the formula for the logarithm of 2, the natural logarithm of 2. So I'll just have to look into this before uploading the result. May the 2nd, early in the morning. And I think I've found the solution to the problem. Going back to the ln2, the natural logarithm of 2, we have this sequence for, or some series for the logarithm of 1 plus x, and for x numerically smaller than 1, it converges absolutely and uniformly on bounded subsets or compact subsets. Nicely. But how about setting x equal to 1? And the point is, it need not be this series that 1 minus 1/2 plus 1/3, etc., that converges to ln2. Maybe it's some reordering of it. And I wasn't able to find out what it was yesterday, but it appears that the solution is Lebesgue monotone convergence theorem, which I believe we all know. I just didn't realize it was the solution. Oops. So we define Fn as the first part of it, so it's minus to nth 1 divided, minus to ith, and then x to ith divided by I. So the first n sums, that's not monotonely increasing. But if we take the even guys, let gn of x be f of 2n of x, then g1 is the sum of these two, G2 is the sum of these four, and I claim that in some neighborhood of unity, they are a monotonely increasing series. I actually haven't made the details. So I believe that shows that ln2 equals this sum. Now how do we write it? Minus to nth, n to minus first. Now we have to apply it to this series. Well, we have an S instead of. And my claim is that when n is sufficiently large, then if we take every nth part of the sum, then all the addends will have the same sign. So b goes from 1 to n minus 1, n minus 1 I said, and then a from 0 to infinity, and we put an outside. 1 divided by an, we can just call it epsilon when we analyze the function. So we define, I want the sum over a to be a monotone, a monotone series from a certain step. It only needs to be from a certain step. And there's the question of the domain. Where do we really sum? We had that in a previous exercise, but I forgot the result. Let's assume that it converges for the real part of S being larger than 1/2, as I wrote. Now this should be a function of epsilon. Of course, f of naught equals the sum of chi of b, which vanishes. So since f is a differentiable function, we have just to show that one of the derivatives is distinct from naught. Then in some neighborhood of naught, it will be to the right of naught, it will have a definite sign. So there's an interval where it's either positive or negative. So let's differentiate it once. So it gives the same, and then times ln of this and times it differentiated. And then let's just put it down here. Nah, let's put it up here. And then times this differentiated, which gives minus b. This is annoying. Well, let's expand this. Or write it in another way. B chi of b ln 1 minus so f of naught simply is this vanishes, this gives unity. I thought it would give a simple, a more simple expression, because when we differentiate this again, we get 1 divided by this, which then gives s plus 1, so it becomes rather complicated. Well, I expected something like the nth, n is a bad number, isn't that? It's okay. The nth derivative at naught was minus to the nth times sum of b to the nth chi of b. That's a little intractable going on from this. But if we assume this result, then if they all vanish, then since the polynomials can approximate any function, we can, many functions, we can, with a finite number of points prescripted, we can go through it. So b point chi of b from b equals 0 or 1 to n, that's easy. And then that sum would be the sum of chi of b squared, which would give the Euler function of n, the Euler-Totian function of n. So that's impossible. So one of these guys will be distinct from naught, and then we will have a neighborhood of naught where this has a definite sign, and that means that from a certain step up here we will have a monotone convergent series, and therefore the limit of the values of chi actually equals the sum evaluated at s equals 1/2. Which was what I wanted to prove. And as it happens so often, these elementary questions, they are actually solved in elementary mathematics, but I didn't always pick it up at the time.